Hello and welcome to the Oxford Online Maths Club, assuming that I've managed to press all the buttons to cause us to be actually live. I'm joined today by Jonah. Say hi, Jonah.
Hi.
My name's James. I'm a tutor at the University of Oxford. Today we're going to do some maths. I hope that's all right on the Oxford Online Maths Club. We're going to talk about prime numbers and also fake prime numbers, things that look prime but are not quite prime. But first, I want to say hi to people who have joined us in chat, because it's not just me and Jonah. We've also got, I can see Miles and Fonzie and Aya in chat. Aya says it's their first time joining live, so hi Aya. It's a good place to start because it's the start of 2024. It's episode 0 on the Oxford Online Maths Club. You might let's grab a bit of paper and a pencil if you want to take notes or write down things that are happening, and you might want to get into the live chat where Miles and Fonzie and Aria are. The live chat is where we do things like catching up with what people are working on, and shout outs, hi Rowan, and anonymous. The nice thing about chat is that you can be anonymous if you want to, and it's also where I run polls like how was your day, so I can find out how people's day was. Jonah, how's your day been?
It's been pretty good. I came back to Oxford today after being home for the holidays, but it's quite a long journey, but it's nice to be back.
Right, you're back for term, of course. Which year are you in now? Remind me.
In my 4th year, so I'm doing my integrated masters.
Right, 4th year masters year. In order to get Master of Mathematics as the qualification. Pretty cool qualification. Cool, right, okay. Chat is voting about how their day was as well. At the moment, it is a 4-star day on a scale of 1 to 5. And the people in chat are telling me about A-level maths exams. And Brazenose have sent Miles an automated survey email, which sounds scary. Do you remember this sort of? So the period of time we're in right now, Jonah, is that people are waiting for offers from Oxford, and there's nothing anyone can do. So we're all just going to learn about prime numbers instead. Presumably, we've got some people in year 12 as well who are not waiting for Oxford offers, and in fact have not applied to university yet. Plus you and me. Here we are.
Yeah, brilliant. Yeah.
Episode 0. Yeah, I think it is episode number 0. We start our sequencing from 0 around here.
Okay.
I think those are our rules. Start from 0. Don't divide by 0. Please don't swear. Those are the rules for chat. Chat's being moderated today by Joseph, who is also a maths student. Good, right, okay. I'm always looking out for people who vote for 1-star or 2-star on this sort of poll, but that is nobody. So I think we should get on with some prime numbers, if that's all right. Jonah, I'm going to throw to you, I think. Can you help us define a prime number, please?
Yeah, of course. So, what is a prime number? Well, a prime number is a whole number greater than 1 whose only factors are 1 and itself.
Okay.
It seems slightly arbitrary that we say greater than 1, but it's not completely necessary, but it makes the maths a bit nicer.
Yeah. Let's get some examples.
2, 3, 5, 7, 11.
Sorry, I said that like it was an exam question or something. Chat, what's your favourite prime number? Yeah. So while I wait for chat to tell me their favourite prime number, I guess I should address the thing in the thumbnail, right? Where some numbers under 100 look like prime numbers, but are not prime numbers. So 91 is a good example, I think, because 91 looks prime to me. I mean, it's not even, first check. It's not a multiple of 3, and it's not a multiple of 5, and around that point I kind of lose interest, and it's presumably now a prime number. Aya likes 13, which is here in the sequence. Chat, I see you putting 39. Somebody said their best prime number is 39, which is a dig at me, because on a previous live stream I told a story where I thought that 39 was a prime number. I think, unless I'm really taking things too personally. Vote for 73. 73 is prime. It's Have you heard this thing about 73, Jonah?
Which one? Is that the one where it's the 21st prime number and then you reverse the digits, you get 37, and that's the 12th prime number?
Yeah, that's the one.
Yeah.
Which is silly, I think, because it's got digits in it, but also brill.
Yeah, I didn't like that.
What is that? Someone adjustment 10,003. Yeah, they they look prime, I guess, because their factors are prime. Everything's got prime factors, I suppose, but 91 is in fact 7 times 13 if you're playing along at home. Okay, lots of cool things about primes, right? You could do prime factorization with them to write anything else in terms of its prime factors. If a product is a multiple of a prime number, then either one or other parts of that product is a multiple of the prime number, and lots of other stuff. Rowan's voted for 101. Go.
One of my favourite things about the prime, the reason we go for prime numbers being greater than 1, like you said, with prime factorization, is so that we have unique prime factorization. Otherwise, that we can add times 1, times 1, times 1 on the end, and we no longer have uniqueness.
Yeah, it would just be a bit rubbish, wouldn't it, if we said, oh, and it's also 7 times 13 times 1 squared as a different way to factorise it. It's kind of not really different. In general, how do people feel about negative numbers in the primes? I guess, Jonah's, you've carefully defined it to be bigger than 1, so that we don't have any negative primes. How do you feel about negative primes, Jonah?
I think you've got to be careful because, I mean, again, we like prime numbers partly because of their unique factorization. If we go to negative numbers, then we can switch the -1 around and all that kind of stuff. I like which number's negative in the prime factorization, then it just has to be very careful. So it's much nicer to think about things when they're positive.
Right. Yeah. So if you start allowing negative numbers to be prime, then you get lots of non-unique factorizations, because presumably you believed -7 to be prime, and also -13 to be prime as well. So you end up with factorizations like this.
Yeah.
Which are kind of all fine up to minus signs, but other than that, yeah, it's just not quite so pretty. Ooh, vote for 97. Anonymous has told me that the link to chat's not working. I think you're correct, I just tested it. Which is, sorry about that, I will fix it after the stream. In the meantime, if you type slido.com and then enter the event code OOMC for Oxford Online Maths Club, you can do that one. Oxford Online Maths Club is not going to turn into 4chan, because although people can be anonymous, chat is moderated. You might notice that there is a bit of lag on your chat message. That's to ensure that nobody is swearing or dividing by 0. There's a working chat link in the YouTube description. If you're on desktop, then you can get the YouTube description up to get to the link. I'm not sure how it works on mobile. If I'm on your mobile phone, then hi. Sorry, I don't know where the links are. Nice phone. Sorry, taken by the idea of being back on live streams, Jonah. It's fun. Right. Okay. I've got Jonah on the stream because Jonah knows a fact about prime numbers, and I'm going to get Jonah to prove it. I'm just checking. Have we done the setup? Have we got everything we need for you to tell them your prime number fact?
I hope so.
Okay. Let's have a go. Then.
Okay. So my prime number fact is known as Fermat's little theorem. I think it's nice to give it a name because then we can refer to it. James did mention beforehand to make the obvious reference to Fermat's last theorem, which this is not. Unfortunately, we're not proving Fermat's last theorem today, although that would be quite fun.
Fermat's got way too many things. It's one of those mathematicians with too many theorems. So many that even if you give them acronyms like FLT, then you could mean Fermat's little theorem, Fermat's last theorem, Fermat's latest theorem for like the hot new Fermat theorem, or faster than light if you can't spell. Right, good. Sorry, it's like obligatory that we have to do a version of this joke that the L can stand for 2 things.
It's a good point. I mean, it's an incredible amount of stuff to do that Fermat did. Given that he wasn't even a mathematician by trade, he was a lawyer.
Ooh, I didn't know that.
Little fun fact about Fermat. Oh, sorry. Yeah, on to my fun fact about Fermat's last little theorem. Is that if we've got a prime number p, and any number a, then I'll speak relatively slowly so you have the chance to write this down on the screen. So yeah,
Thank
prime
you.
number p and any other whole number a, then a to the power of p minus a is divisible by p, meaning that a to the power of p minus a is equal to a multiple of p. So when we divide by p, we get a whole number. We're assuming here that we're just going to be working. I mean, I say the integers. We'll probably just stick to the positive integers. So everything in here is a nice positive integer. We're not dealing with anything unpleasant. And yeah, I think it's a really beautiful fact because I mean, I don't know about you guys, but the obvious thing I'd think about doing when looking at something like a to the p minus a, maybe factorizing it or something like that, or maybe trying to look at roots of it as a polynomial equation. All that stuff doesn't really get you anywhere with this really nice little theorem. So I think it's a very beautiful thing and something that we're going to do like quite a nice aesthetic method to have a look at it.
We've got a proof, I think. It's maybe worth, I don't know. I think it's just, the reason I think Fermat's little theorem is cool is that it's true for kind of any number a, including implausibly large numbers. Those powers get really big really quickly if you put in large numbers, and somehow this thing is just always true, even for those very large numbers, which of course Fermat had no way to calculate and to operate with. If you put in like a is 2024 and p is 101, then I don't know what that number is. It's huge. Rowan in chat says, did Fermat bother to prove this one himself? Which is incredible shade thrown at Fermat. It's a reference to Fermat not always showing his working out or backing up his claims with actual proof. We're going to do a proof. I don't think it's the proof that Fermat would have done. Is that right?
I mean, I have no idea what proof Fermat actually did, but this is quite a more demonstrative proof. The purpose of this proof is more like to make it enjoyable. It's fun. It's an interesting proof.
I'm making a note to look up whether Fermat actually proved this one. It's not always the case that you have to prove something to get your name on it. See also Fermat's last theorem definitely didn't. Anyway, never mind. By the way, my notes at the end of each episode, usually the next day, I go and write some further reading notes based on whatever we discussed on the stream. If you want to catch them, they are on the Maths Club website. There's a link on screen. I know that the link doesn't work on screen. There's a link in the description as well, and hopefully people will find the further reading notes, which this year my New Year's resolution is to actually try and write them on time and properly and get them on the website. Didn't totally manage it last year, but looking at whether or not Fermat proved Fermat's little theorem. Anyway, the important thing is that Jonah is about to prove Fermat's little theorem, so I think I should let you do that. Sorry.
Sorry. Okay. We're going to do a slightly more interesting method of thinking about this proof. What we're going to be looking at is we're going to look at necklaces. And when I say necklace, what I mean is a circular string with colourful beads on it. Perhaps not what your ideal necklace would look like if you receive it as a Christmas or holiday present, but this is what I'm going to mean when I say necklace. So I will be thinking about string with colourful beads on it, and in reference of what we're trying to prove, my necklace is going to have p different beads on it. The number of beads is going to be p, the prime p, and I'm going to have a possible colours to choose from. So whatever our number is for a, hopefully if you were trying to think of a different colours, a would be pretty small, because I don't think, like James said, I don't think I could come up with 2024 different colours. But it's more like a theoretical thing. These are different, we've got a different colours and p beads on this beautiful necklace that we're trying to make. And the question we want to consider is, how many necklaces are there with p beads of 8 different colours that have at least 2 different colours on them? So that means we're going to ignore all necklaces that have only one colour.
Okay, and you're ignoring the kind of boring ones, right?
Yeah, exactly. I mean, I'll make a very clear reference to when we make it clear that we're ignoring the ones that are just a single colour.
Okay, I'm going to call those monocoloured. I hope that's all right. Bringing in a new dictionary word here, but monocoloured. ones. So actually the one I've drawn is way out because it's boring, it's monocoloured. I need... How many colours do you want me to do? So I've done P as 5 in my picture.
At least 2 colours works.
At least 2. Shall I be brave and go for 3?
Oh, that would be brave.
Okay. And is the rule... Do I have to use all of the colours?
No, not at all. So, I mean, you've done a necklace where P equals 5 and A equals 3 is just a monocoloured one.
Oh, right, okay, it's just too boring. But is this interesting enough for you?
I do like that one. It may benefit you later on in the proof to be using 2 colours purely because otherwise you're going to be jumping back and forward to choose colours.
Oh no, I've committed to it. Hang on, I'll just commit to like this. Okay, pink and blue.
Okay. Pink and blue, lovely.
In case anybody in chat is pink-blue colourblind, I'm going to put a spot on each of the... Oh, I regret this. Now I am 3 colours. Anyway, I'm putting spots on all the light blue ones, just in case. There's one person in chat who's pink-blue colourblind. Okay, it's a counting problem, I guess. We've got to count how many of these necklaces exist. Really sorry about the background noise, by the way, if you can pick that up. I'm right next to a sort of building site, so that's fun. I think somebody in chat's just said they saw this in... Somebody in chat said they saw this in further maths, which is amazing. I didn't know this in some people's further maths course. Someone in chat, please, who maybe hasn't seen this in further maths, can you help with Jonah's question? Do you have any idea how many of these necklaces there might be?
Might be worth adding, because I'm going to add something where we say certain necklaces are the same, so that's possibly worth mentioning.
Okay. Oh, I see. Sorry. Okay.
So I think one important thing I want to mention is that we're going to say 2 necklaces are the same if they're just a rotation of each other. So if I can rotate one to get the other, that is an important fact that I want to mention here. But unlike with normal necklaces, if you rotate a necklace to get an upper necklace, they're the same necklace.
Oh right, okay.
Unlike with normal necklaces, what we're going to say is that if you flip over the necklace so you get the mirror image, that's not the same necessarily. It's only 2 necklaces are only the same if one's a rotation of the other.
Oh, okay. Rotations count as the same. Well, now it's quite hard.
Yeah,
I was feeling confident about this because, like, you have some choices, and in A level I learned a lot of stuff about having separate, independent choices. I wonder if.
Well, actually, my first question I was going to ask the chat is, if instead of looking at it as a necklace, say it was just a strand, it was just a string that's not like just one string in a line with P beads on, each which has A possible colour choices, how many possible strands are there, if we call these strands? How many possible are there? And also, how many are there that aren't monocoloured? That is an important thing we want to know first.
Okay, so if I unwrap my bracelet, blue, pink, blue, blue. Okay, this is a good thing to explore, I agree. Rowan in chat says that Fermat maybe didn't prove this one either, which is just hilarious to me. There's a Fermat quote on Wikipedia: "I would send you a demonstration of it if I did not fear going on for too long," which is starting to look like a kind of MO for Fermat, right?
Yeah, it's almost like he doesn't actually prove anything himself. He just states things that seem like they might be true.
I would prove it, but a dog has, he will never believe. For verily, a dog has. The strangest thing. People in chat are telling us. Mike says A to the P. Fonzie says PCA, using C for the choosing notation that I remember from A level. There's an A to the P over P, but maybe minus some other repeats. For somebody thinking about overcounting, dividing, and trying to allow for any repeated ones. Yeah, there's a call in chat to maybe refer to this as Jonah's little theorem. If you successfully finish this proof,
that's a big hit.
Just stop referring to Fermat.
Yeah, no,
we're doing all right. We got some ideas.
10 minutes before the end of the proof, I'm going to say that I'll leave the rest as an exercise to the listener.
Oh no! Oh no! We've got chat on side as well. Chat's been very helpful. Chat's given us several suggestions of how many ways there are to colour in this strand. So let's be clear. You're going to let me just pick any. If we're doing strands, I can do sort of anything, right? I don't have to do 3 blue, 2 pink.
You can do whatever you like as long as you stick to the rule that we've got P beads and A possible colours, and we've assumed that it's probably worth noting that I assume that I've got enough of each colour that I'm not going to run out. It's not like, oh, I can only use 3 blues and 1 pink, or we don't have a finite number. Or we can, we just don't have a number where we're going to run out.
I think we left the realm of physical concerns when you told me I wasn't allowed to turn it over. So yeah, so people are saying 5C2, which is a good suggestion. 5C2 is the number of ones that look just like this, with 5 beads, 2 of them pink. And then I see an anonymous person has also said that you should add up the other ones, right? Because there are like 5 choose 3 that look like this with 3 pink beads. And I suppose there's also 5 choose 4 with 4 pink beads. 5 choose 1 with 1 pink bead.
There's actually a pretty nice proof of the fact that if you sum up the choose functions, you get 2 to the power of, well, in this case, 2 to the power of 5.
Yeah, there's a nice sort of choosing thing. I've written 2 pink twice. That's not an intentional mistake. This sort of choosing actually, this is a good way of breaking it down into cases. I'm leaving out 0 pink and 5 pink because we don't want a monochromatic one. If you add those together, then yeah, you get the answer. But this sort of choosing is a good way of breaking it down to cases that gets much harder if there's a third colour. So far I've written A equals 3, but I've only declared 2 colours of beads. So I'm going to go with A equals 2 so far.
I think maybe a helpful way of thinking about it is you think that for each bead you have A choices, and the choice you make for each bead is completely independent of any other choice. So I make my choice out of the A possible colours for bead 1, and then independently I can make the next choice for bead 2, and then independently for bead 3, and so on and so forth. And with counting, we can do some nice stuff when we put independence.
Right, okay. So with 2 colours you want to do something like this, adding together choices, but with 3 colours maybe it makes more sense to think about those as independent choices you're making for each bead in turn. I'm trying to draw a more complicated case. I don't know what I'm doing. I think I'm trying to draw a 4 bead one at the same time as talking. So what's the answer then? What's the answer to how many of these are there?
Yeah, so for the first bead we have A choices, so that's A. Second bead we have another A choices, and we've got 2 independent choices, so you may know from combinatorics we multiply those together, and so on, and we do that for all P choices, so that gives us A to the power of P, which is what we're looking for. And as you correctly proved in chat, that this proves that if you add up the choice functions, but you're only doing this for 2 colours, so A is 2, you'll get 2 to the power of P.
I think I saw Mike a while ago say A to the P for how many of these there are. Miles, or anonymous person, sorry, has just said 2 to the P. But then some subtraction. We got to allow for those monochromatic ones. Chat has not missed this fact that there's some. If you just do these independent choices, then you're not keeping track of the possibility that you, oh dear, accidentally made the same choice every time. How do we allow for that?
Well, the fortunate fact is that it's easy to count the number of monochromatic strands because we have A colours, and therefore there are A different monochromatic strands. We've got 1 for each of the colours, so we can just subtract A, as I can see people in chat have very clearly mentioned.
People in chat are on this. So you subtract the A monochromatic ones. I wish I'd said monochromatic the first time. It's a much cooler word. I'm going monocoloured again. Consistency. If only I remember the word chromatic. A monochromatic, a monocoloured. What are these, strands?
Yeah, I've called these strands, and then we're about to go and look at how does the necklaces relate to these strands.
Okay, so we're still inside this, but first. I'm putting some brackets around this, but first. Counting. Okay. Rotations count the same was a comment about the necklaces. Got it. Okay.
Brilliant. So
Okay.
the next step, okay, well, how do these necklaces relate to these strands? Well, what we're thinking is that if I have a strand of a necklace of P beads, that gives me P points where I could cut that necklace and turn it into a strand of length P instead.
These are
So, yeah.
scissors.
I very
Okay.
much like that graphic a lot. So the question is, how many? So say I cut this necklace. So I've got my necklace. I cut it in the P different places. Do I get P different strands, or at some point am I going to get repeats of strands? Perhaps I maybe suggest one that maybe doesn't fit, because I mean we've assumed P is prime here, and we're going to go back to P being prime. But for example, were you to draw a necklace of 6 beads, and maybe the colors can go blue, or blue, red, blue, red, or you choose the colors however you see fit
Okay.
for easy purposes.
Blue, red. Blue, red. Blue, red. Oh, I see. And you're giving this an example where there's a sort of more complicated relationship between strands and necklaces, because cutting it at that point is the same thing as cutting it at that point.
Exactly. So the problem is that I want to show that if my necklace has a P number of beads where P is prime, then and I cut it at all the different places, that's going to produce P different strands. Well, clearly, in the case when P is not prime, for example, P equals 6, I can have this kind of issue where I cut it in 2 different places, but they produce the same strand. So we need a sort of idea of how to go about solving this. And I think a lot of you might have heard of a kind of like proof by contradiction. This isn't going to be a full proof by contradiction, but we are going to suppose that if I were to, so I take my necklace, it's got P beads, and I suppose that if I were to cut it in 2 different places, say K beads apart, that they would produce the same strand. I think that's a good start for our proof by contradiction. It might be hard for me to explain without drawing anything, but I...
Oh, okay. I'm going to draw something, don't worry. I was just labelling out what we've done so far,
No.
sorry. We had strands over here, okay, and you're going to tell me that if P is prime, then these different cuts are all different strands.
Assuming our necklace is not monocoloured.
Chat spotted that the monochromatic ones, wherever you cut a monochromatic one, you always get the same strand, which is why you've excluded them. Okay, ignore the boring monocoloured ones. Right, clever. Okay. Right, let me try and draw your... So you're cutting your prime number of beads, and you're cutting it at 2 points K apart. I'm going to make prime a little bit larger. Cut it at 2 points K apart.
And we're going to suppose they make the same strand.
Okay, I'm reading around this way. I'm reading around from here.
Okay, and I'll call the bead at the first cut 1, and the bead at the second cut K plus 1, because I'm just numbering them as we go round twice. So we've assumed these are the same strands. So what we've got by our assumption is that bead 1 is the same color as bead K plus 1, and bead 2 is the same color as bead K plus 2, and bead 3 is the same color as bead K plus 3, all the way up to saying that bead K minus 1 is the same color as bead 2K minus 1. So what we've proven here, what we understand here, is that the first K beads, or as we go around cyclically, are the same color, form the exact same pattern as the second lot of K beads.
What's this number here? Sorry, this is 2K minus 1.
Yeah, we've got K minus 1 and 2K minus 1.
Oh, yeah, sorry.
Yeah, sorry. Oh, yeah, K and 2K. Sorry, no, you're right. K and 2K.
Not sure I am. Counting chat.
Yes, the first K bead. So it's
I've
1
added
to
K minus 1.
And then so it's 2K.
2K, right, good. K and 2K, thank you. Counting is not a strong point for me. Continue this pattern.
So what we've got is that the first K, the pattern of the formation, the string of colours formed by the first k beads is the same as the pattern of the string of colours formed by the second k beads. But then we can continue. Because of the same logic, just continuing on, k plus 1 is the same as 2k plus 1. But k plus 1 is also the same as 1, so therefore 1 is the same as 2k plus 1. And 2 is the same as 2k plus 2. Hopefully, I know we're getting a lot of algebra here, but you can see where I'm going, that this pattern of k, this string of k colours, is just going to keep repeating round our necklace. And the end goal I'm trying to show here is that if this were the case, then we have a repeating pattern of k colours going round our necklace, and because we've got p beads, that means that we've split our p beads into chunks of size k that repeat as we go round, and therefore k divides p.
Cool. Split into chunks of k. Chunks is a good word here, I think. Chunks of size k.
All of which are the same, have the same pattern,
Yeah. There's kind of something funny that happens when you get round to the end, right?
Exactly. Otherwise, we'd form. We need, again, by the same logic, we need this k to go nicely into our p. Otherwise, by continuing on as we're doing, we're going to start rewriting the colours. So we're going to have one being the same as a colour as a different one, and it's going to go awfully wrong if k doesn't go nicely into RP.
Or if it's monocoloured, because if it's monocoloured, then you can cut it anywhere. Okay.
So what we show here is that by continuing on this pattern, that k must go into p because we've divided our p beads into k. But as you said, I mean, we know k, 1 divides everything. So 1 is a perfectly good solution here for our problem. If we could split it into chunks of size 1, and if each of those chunks are the same colour as every other chunk, i.e. if our necklace is monocoloured, then yeah, we have this thing where we could cut it anywhere, or we could cut it at different places and produce same strands.
Yeah, I think it divides. I'm worried that you might have to go round the circle several times before it matches up with itself. But I agree it will happen. That eventually you'll keep going round and round and round until it matches up. And k will divide. What am I going to do? What am I saying? No, ignore me. I'm going to agree with you.
You're going to keep going up in multiples of k, and eventually your multiples of k is going to get bigger than p, and then you'll go straight back to the beginning again, and either you'll rewrite yourself, or, I mean, we're going to come to a contradiction, or we're just going to need to line up perfectly with where we started, which will mean that k goes perfectly into p.
Right, okay. There's this kind of repeating pattern, and you just can't do repeating patterns when you've got a prime number of beads, because primes don't have non-trivial factors.
Exactly.
Go on the p beads k times then at the beginning. Yeah, the thing I said about going around multiple times was not a useful thing to say. I think I was ignoring the problem when I said that. Imagining some sort of overlapping pattern that overlapped with itself. Sometimes I've seen people say this where you take the minimum possible k. So for the contradiction, you take the minimum possible k, and then you get to do a tiny little proof by contradiction where on your way round, if it doesn't match up, then it overshoots a little bit, and hey, you get to stop the pattern here, but that means you have a sort of smaller unit of the repeating pattern. So I've seen it phrased like that before as well, which sort of marries up the idea about maybe overshooting a little bit to prove that it divides at the end.
I like the minimal proof. I think given a nice piece of paper, an algebraic proof of this could be far more aesthetic. But I like the drawing proof. It's far more interesting to go, look, it's probably true because we've drawn a lovely picture.
No, I think we've done enough algebra. Chat can let us know if they want more algebra. This could be the only YouTube live stream with people in chat asking for more algebra. Possibly not even this live stream wants more algebra though. We'll see. Somebody in chat has tried to use one of my Twitch emotes, which is fantastic stuff. Love to see it. The Twitch emotes don't work on YouTube, sorry. I'll draw the wow face for you. Somebody has tried to react like this for you. Two people in chat want more algebra. Cool. And that was really quick. I shouldn't have encouraged them.
Yes. Well, so the key thing of what we've proven here is that if we had a repeating pattern, if we had different strands, so we could cut our necklace at different points to produce the same strand, and say I like the minimal idea of where we take k to be minimal, then the point is that we'd reach a contradiction unless k goes perfectly into p, therefore k divides p. But we chose p to be prime, which is a clever thing to do, and so clearly our k is quite restricted. I mean, I think the key, yeah. So either our k is equal to 1, as we said above, at which point that means we could cut our strand, we could cut it anywhere. It's a repeating chunk of size 1, which basically just means every bead is the same color. Or k is equal to p, which means we've actually said we can just go round and cut it in the exact same place as before. So that's not actually saying anything. K equal p is not an interesting case because that's just cutting it in the same place twice.
Yeah, I guess, just for the algebra fans, the missing line of algebra that is in my head, which I will do here, is this. No, what is this? What do I want here? Oh my goodness, I can do this. So you go round by p plus, no, I want this. I can do this, I believe in myself. Yeah, cool, okay. Yeah, there is an n such that after you've done n units of the repeating pattern of size k, you get round the loop to somewhere between the p plus 1th bead, which is secretly the same as the first bead, and the p plus kth bead, which is secretly the same as the kth bead. If you do that, then you can now argue that the pattern starts again from the nkth minus pth bead, which is a smaller example of where the repeating pattern started, unless this thing is 1 or k or something. Oh, goodness me. Maybe I want to exclude 1 and include k. And I sort of think that we should have started counting from 0, but too late now. Rules of the live stream.
I think half of what I do when I do my combinatorial maths is just go, I probably should have started counting from somewhere else.
Yeah, I probably should have counted from 0. I said it at the start. Cool. Okay. What are we doing? What was going on?
So back to what I was trying to prove. So we've got our necklaces, but we've assumed they're not monocolored. As so we have our necklaces. They're not monocolored, and therefore we could cut them in p different places to create different strands.
Right.
So therefore, and then we go back to our number of strands. Well, we've got the number of strands, and our number of strands is a to the p minus a. And so it's obvious that if I connect a strand, connect the ends of a strand, I get a necklace. But at the same time, if I cut the necklace in p different places, I get p different strands. And therefore, the number of necklaces that aren't monochromatic of p beads in a different colors is a to the p minus a, all divided by p.
That's amazing. You've got p strands that corresponds to one necklace. And for each necklace, there are exactly p strands. That's what you've proved by carefully chopping them in different places. For each necklace, you can chop it in just the right places to get exactly p strands. And for each of the strands, you definitely get a necklace when you tie it up, which means that for each necklace, there are exactly p of these. You've separated out, I guess, the strands into this big sea of a to the p minus a, huge number of strands. You've separated them out into groups of size p, which proves that it's a multiple of p.
Exactly.
Brilliant stuff. I like it a lot. Maybe people in chat spotted where you were going or what the relationship was as soon as the a to the p minus a turned up. That being the number of strands, and the fact in the middle that it was well p. Okay, let's do a lightning speed recap of the whole thing, which is something I like to do. I like to do fast, slow, fast. When you see something, first you see it quickly, then you do something quite slow in the middle, which usually for me, it would mean go away and think about it, and then you try and recap it fast. We haven't got time to do the slow version, where you go and rethink about all the steps of what's happening. But I think the fast, quick version at the end is helpful to do now to give you an idea about what's going on there. Jonah's main idea, I think, is to think about these necklaces, these loops of string, as having some relationship to strands, like this, straight lines of string. The relationship is that you can join up the strands to make a necklace. The strands are relatively easy to count. There are a to the p minus a of them if you ban the monocoloured ones and you make choices along the strand. The tricky thing is that strands don't correspond to necklaces one-to-one, because you can cut the necklace in different places to make different strands. Or if you like, you could rotate the necklace to match up with your scissors. Rotations count as the same necklace. You could rotate the necklace and then cut it, and you get different strands like that. But because p is prime, you always get exactly p different strands out of your different options for cutting the necklace. You never get a repeating pattern like this. And that means that for each necklace, there are a huge number of necklaces, I guess. Not actually sure we do have a number for them. There are exactly p of the strands, joining them together, a kind of group of p of them. That means that there are a to the p minus a all over p, the number you just said, I've caught up with you, necklaces out there. And that's a whole number. I love this proof. I love a proof where you do a calculation, like a counting problem, and then it's an interesting fact to say, oh, and that's obviously a whole number. Because it's a counting problem, right? It's got a division by p. It's really not obvious that that's going to give us a whole number, but it's the number of necklaces that exist, so it's got to be a whole number. Good. I like this a lot. Mike is happy, Herb in chat is happy, Ira in chat is happy. Good. I'm glad that people haven't... If you haven't seen this before, I think it's fantastic. It's really good example of some sort of like visual proof in mathematics. Okay, there's a bit of algebra in there to check that p being prime is the important thing. And that's what I want to talk about for the last 10 minutes of the show. After a quick ad break, I have a slide for this. Let me load my slide. Ad breaks are a thing we used to do in the maths club. They went away for a little bit, and they're now back. So this is a chance to have a breather, maybe grab a cup of tea or something while I run break. Come on, please load. I'm so pleased with my ad break. The ad break is always a problem to do with addition, and this one introduces the idea about modular arithmetic. So when we're talking about things being a certain number more than a multiple of p, you end up using the phrase more than a multiple of p, x more than a multiple of p, quite a lot. There's this short notation for it, where you write something like this. Here I'm writing b mod p to say, aha, this is b more than a multiple of p. It doesn't look like I'm saving very many pen strokes or characters there, but it adds up. Also, because it's kind of this equivalence relation, it's not equality. A is not equal to b. They're just the same. They have... Each of them is the same up to multiples of p and their difference. I'm going to have one more go. So if something's one more than a multiple of p, you might say, well, p plus 1 and 3p plus 1, those are both examples of things that are 1 more p. So one more than multiple of p, 1 mod p. So I might say that 3p plus 1 and 2p plus 1 are equivalent, mod p. Loads of arguments that you get in school where you talk about like odd and even numbers, or you talk about all these cases for like 8n plus 1, 8n plus 2, 8n plus 3. They're just much faster if you can say things that are equivalent to 1, 2 or 3, mod 8 or something like that. Yeah, sometimes people say have the same remainder. I'm trying my hardest not to say remainder. Jonah, why am I not saying remainder?
I mean, because the problem is we say that two numbers are equivalent mod p because they. If I were to use the word remainders, it would be because they have the same remainder when divided by p. But that doesn't mean that we're always looking at remainders. We could, for example, when divided by 5, 12 and 7 both have the same remainder, therefore they're equivalent, but neither of them is less than 5, so neither of them is a remainder when divided by 5. So it gets slightly more complicated if you start talking about remainders.
The word remainder comes with, this extra baggage that they're supposed to be small numbers, whereas 2p plus 1 and 3p plus 1 are both like massive. So I'm trying my hardest not to say remainder. People sometimes say they have the same remainder mod when you divide by p, which is kind of acceptable. The fact on the board is one of the first things you prove when you learn about this, which is to prove that addition works. That you're throwing away information here if you ignore multiples of p. Does that actually respect addition? So, ad break, there you go. This season of the Maths Club is supported by the Mathematical Institute at the University of Oxford, as always, and also by Jane Street. You can find out more about Jane Street on the Oxford Maths Club website. Right, good. Okay, that was an ad break. Is the addition joke still funny, even though we have like an actual supporter now? Jonah, let me know.
I found it quite funny because when you said ad break, I was expecting it, but so it caught me by surprise, and I did enjoy it.
Is it a sort of double part? Is it sort of double surprise if it turns out you think ad break and then you see it's addition and then it turns out that it kind of is an ad? Does it work on two levels? Can I get you twice? No, I'm not really sure I can.
Yeah, no, I think once is maybe pushy. Yeah, I think twice might be a bit far.
Maybe that joke was funnier in the past. Right, let us know in chat. Okay. So an example of something that you might write using this mod notation is that you might write is a to the p is a more than a multiple of p. And I'm just telling you this because if you look this up afterwards, Fermat's little theorem, it might be using this notation. So I just want to acknowledge that this is the same thing Jonah has said using slightly different notation. If I read it out, it says a to the p is equivalent to a mod p, which means a to the p is a more than a multiple of p, which is the same thing as saying, that a to the p minus a is a multiple of p. But look how long this takes me to write.
It's also nice to write that. I mean, because as you showed, though, as you said, addition works nicely, and because addition works nicely, followed quite quickly that subtraction works nicely, and then we subtract a from both sides of this, and we've got a to the p minus a is equivalent to 0 mod p, which is quite a nice thing to write. 0 mod p is lovely. Everyone likes 0 mod p.
0 mod p normally means you're onto something, that something is a multiple of something else. Oh, I need to do a big 0 here. There we go.
I mean, the cliche thing to say is think about your clock. You've got your clock, and that you can think about the time as modulo 12. I don't like going on to that too much, but because again, you start thinking about remainders, and you start thinking about when you think modular arithmetic, you think it must be less than 12 or something like that.
People are really big on talking about clocks when they teach modular arithmetic. Sorry, this is now us just thinking about the times we've learned modular arithmetic, which is weird because people already have strong opinions about clocks, right? And 24-hour clock versus 12-hour clock. People have a kind of intuition that one of those is correct and one of them is wrong. People feel, well, how do you feel about the 24-hour clock? People just do not feel happy about 27 o'clock being, quote, the same thing as 3 o'clock. It's just like, doesn't feel right. People in chat are divided on whether or not the addition pun worked. Good, okay. Okay. So, there's this idea. So if that was this thing's true, this is true if p is prime. Forgot to say, very important. There's this idea, can we reverse this? Oh my goodness, the writing is getting a lot worse. 2 seconds, sorry, while I try and do something about that. What am I going to do about that? Write better, I think. Sudden influx of skill. No, it hasn't happened. Yeah, come on, there we go.
I can read it.
Thanks, Jonah. Can we reverse that? So, if you go out there and you take all possible numbers a,
Did you mean to do p to the minus 1 to the p minus 1?
No, I did not mean to do p minus 1, thank you. This is why you're on the stream, Jonah. You can read my handwriting and spot mistakes. Perfect.
I like being a fact checker.
If a to the p for all a, so you go out there and you calculate a to the p for all values of a, is p prime. Hi, Oscar. Oscar's here from a different time zone. So this would be quite good because, believe it or not, this kind of large power, testing it for different values of a, is something that's actually not that hard to do. There's not, you test it for a few of them and then you can infer for other ones. You can do some tricks to try and check this for all values of a. So this would be really nice because if this is true, then we could do some sort of test and then find out whether p is prime or not. Unfortunately, the answer is no. This is not true. There are some counterexamples. So a good thing to do now would be for me to throw to chat and see if we can find any counterexamples. But unfortunately, the counterexamples are quite hard to find, and we've got 8 minutes until 6 o'clock at the end of the stream. So a counterexample would be a number p that's not prime, but whenever you do a to the p, you get a more than a multiple of p, a mod p. Jonah, do you know any counterexamples to this?
I know two. I think the smallest one is 35, I believe.
Oh, I don't think 35 works. I can't remember why. Now it's on me to try and prove why 35 doesn't work.
You might be completely right. I thought the smallest one was 35. I may be completely wrong.
Now I have to counter your counterexample, right? I have to show that's a non-counterexample by finding a number.
If I just said like the taxi cab number, would that be easier? Are you prepared?
We're getting there. I think the smallest counterexample is 561, which is a fair bit larger than 35. Oh, what do I check for 35? I really don't want to work out 3 to the power of 35 on stream, Jonah.
Yeah, I do apologise. Yeah.
The powers go very large, very fast. Also, I said it was easy. The next smallest counterexample is even larger, of course, and then the rather lovely 1729.
I see that 35 is a quasi-Carmichael number.
Oh, great!
Yeah.
just for my entertainment, Jonah, what does that mean?
It means that it's almost a Carmichael number. It means it's almost one of these, but it works slightly differently. I googled it and it said quasi-Carmichael number, which means it's very, very close. So, apart from this, that's all I'll go into because I have not read through this Wikipedia page.
Chat's working out 2 to the power of 35 for us. They claim it doesn't even work for two.
Oh,
but since 2 is approximately 10 to the power of 10, my calculator can't handle it. Romans tried p equals 0, which, yeah, it is problematic, I think. Yeah, p equals 0 is problematic because you're thinking about the difference being a multiple of 0, which is dangerously close to dividing by 0.
From what I'm seeing from quasi-Carmichael, just purely for interest, it seems that I think the way with Fermat's little theorem, it's p minus 1 when you do to the power of p minus 1. For quasi-Carmichael numbers, it's p plus another number, any number. And for 35, it's apparently p plus 1.
Alright, okay. That's nice. It's a slightly different equation. It's so weird that you knew the number 35 was special and then had to look up the obscure property that 35 had, and then also that it had some obscure property? What's going on there?
Not the first time I've talked about Carmichael numbers, but clearly might be the first time I have. I've realised that I've got found the smallest Carmichael
Right,
number.
I feel like we've crashed sideways into Carmichael numbers, but here we are. I've got a couple of facts about Carmichael numbers that I wanted to tell chat. Maybe Jonah is going to tell me more facts about quasi-Carmichael numbers in a second. Carmichael numbers, relatively recent. I mean, we've known about prime numbers for actually ages, but we haven't known any examples of Carmichael numbers until relatively recently, a few hundred years. And the proof that there are infinitely many of these, which, by the way, there are infinitely many of these, like there are infinitely many prime numbers, there are infinitely many of these. That proof was in 1994, which I think is extremely recently because it's within my lifetime. I'm aware people watching in chat might not be within your lifetime. I won't ask Jonah, is 1994 within your lifetime because I'll feel old. And there's various other kind of things, analogues of facts about prime numbers that are only being proved about Carmichael numbers relatively recently. There's a fact about can you find a Carmichael number between n and 2n for large values of n? So for small values of the n, the answer is just no, because there's just not very many of them. Here are the smallest ones. So you can think of some values of n where there isn't a Carmichael number between n and 2n. But for sufficiently large numbers of n, once you make n large enough, that interval gets larger, because 2n take away n is large. It gets large, but it also gets very far away. So if you're looking for Carmichael numbers in an interval that's large and far away, we know you can always find a prime number there, but the proof you can always find a Carmichael number in that interval is a bit harder. They're much rarer than prime numbers. That proof was in 2022, which is, I suppose I now have to say 2 years ago, because we've just ticked over into 2024. The definition of a Carmichael number is one that satisfies this equation. I suppose probably bigger than 1, and a to the p is equivalent to a mod p. So kind of the thing with the bracelets, that somehow, although there are some repeating patterns within the bracelets, you somehow get lucky. There's something to think about there. When you try to reverse the proof, or when you try to do the proof for a non-prime number, the proof doesn't quite work, but the result might still be true. That's quite hard to get used to in mathematics, I think. You've got a lovely necklace proof, and you've been careful to say, aha, this doesn't work if n is 6. This doesn't work if n is 561. But then weirdly, the result can still be true in those cases. Or worse, it could be false for n is 6 and true for 561. Stream's not over until I factorise 1729, I think. And I know a trick for this. So you said taxicab number. Do you want to tell the taxicab number story?
Oh yeah, the Ramanujan story. I mean, as many of you might know, Ramanujan's a famously brilliant mathematician who absolutely incredible beyond understanding. I think it's Hardy that came to him. I think it's reportedly Hardy that came to Ramanujan whilst he was lying in hospital, and just to kind of spike his interest, said, "Oh, the number of my taxi cab was number 1729. I don't think that's I can't think of anything remotely interesting about that number." And Ramanujan immediately replied, well, that's obviously the smallest number that can be written as the sum of 2 cubes in 2 different ways.
As you do. Have I got them right? There we go.
Lovely.
I've got a little illustration of this scene. So Hardy says 1729, and Ramanujan says, sum of 2 cubes in 2 different ways. We can actually use that to factorise 1729 in this following kind of daft way. 10 cubed plus 9 cubed is the sum of 2 cubes, which not many people know this, but the sum of 2 cubes factorises in kind of a similar way to the way that the difference of 2 squares factorises. Mike is ahead of me in chat. It has this factor of 10 plus 9. There's this pattern. A plus b, a squared minus ab plus b squared. which is factorization into non-trivial numbers. In fact, this one is 19 times, I believe that's 91, which is, factorization not into primes, but into other things. Mike's ahead of me in chat and has typed out a different factorization. Brilliantly, Mike's other factorization shows that from this one, that 1729 is also 13 times, oh gosh, what is this? 144 take away 12 is 132, 133, something like that. And then I suppose just to bring this full circle as we wrap up, the fact that it factorizes like this with a 13 in means that this factorization, it's also a multiple of 13. 19 is clearly not a multiple of 13, so 91 must be a multiple of 13. So you can use these two sums of two cubes facts to demonstrate that 91's not a prime number. So if you can't remember how to factorize 91, here's a clever way to remember. Write out sum of two cubes in two different ways. Go for it. Rowan had to do something like this in a stressful situation once.
We've got to make sure they don't misstate it or something like that, because if they go for the smallest number, that could be written as sum of two cubes of whole numbers. You could go like 0 cubed plus 0 cubed and 1 cubed plus minus 1 cubed.
You got to say non-negative. Is that it?
You've got to say got to say non-negative. I mean, with cubic equations, you can always find nice cheaty ways with negative numbers because they can cancel each other out.
Lots of numbers can be written as the sum of two cubes. For example, 2 can be written as the sum of two cubes. Sorry, I thought I was going somewhere with this, but I've just written out that 1 plus 1 is 2. Good. Okay. I'll have to put a link for me to read as further reading, which reminds me that at the end of the live stream, I always say that we try to post further reading on the Maths Club homepage at some point. If you want to find out more about Carmichael numbers or Fermat's little theorem, or just other facts about numbers, might throw in some random number theory links in there as well. Herb says welcome to OOMC, and if it's been your first time on the show, welcome to you wherever you're watching. I have a script for the wrap up. I kind of don't want to do my script. I'm going to get Jonah to do the wrap up instead. Jonah, anything you want to say at the end?
No, I mean, I think I did like that we came full circle. It's very nice that we came full circle, and I mean, obviously this has some lovely properties in number theory. Modular arithmetic is a really great area of number theory that I really recommend people going to look into because it has some brilliant properties. And I mean, this whole talk, we agreed at the beginning we'd really try and avoid the word group. But I mean, it's definitely worth mentioning that all of this, if you think about it in terms of group theory, is far, far easier. And yes, that is a shameless plug for my other, I mean, I've done many OOMC videos now, but one of them is on group theory, which by no means solves this problem, but is very interesting nonetheless. I think, at least I think anyway.
Yeah, so you were on the show a couple of years ago now to do group theory.
Yeah, this is my fourth time.
This is your fourth time on the show. Oh my goodness. I should have been counting. Counting's still not my strong point. The advantage of learning group theory for things like this is that you learn big general theorems, which let you write down as a kind of example of this theory, Fermat's little theorem. So like we have examples of the theorem being used, you have examples of a bigger theorem, which spits out theorems.
I feel bad saying that, yeah, it's a useful fact that this is an immediate corollary of something called Lagrange's theorem. Maybe I won't go into it, but like it's an interesting fact.
This is a good plug for university mathematics, right? Which is
exactly
something I try to do. Like if you want to find out more about Lagrange's theorem, then I highly recommend some sort of university mathematics course. That's a good way to learn Lagrange's theorem. Yep, good. Someone's here from the Step Up New College Residential. Hi. Welcome to. Look at the camera when you say hi. Good. Right. Cool. Okay. I'm going to call it there. If you want to see more of this, we're back in 167 hours for another episode. If you want to see more of me, I do another stream on Twitch. If you want to see more episodes of this show, there are about 70 previous episodes that you can get on the Maths Club homepage, other live streams on this channel. We're almost at a perfect number of subscribers. We don't ask for subscribers. The number doesn't mean anything, except if it was a perfect number. I think we can all agree. That's pretty cool. After that, I think I might be asking people to unsubscribe because we're never going to make it to 33 million. So trying to hover around the largest plausible perfect number is where we need the channel to be, I think. The script, I don't like the script. I'm going to write a new script that's less canned. Good. Look, isn't it better not having a script and just waffling for 5 or 6 minutes? Thank you for coming on the show, Jonah. Thank you for watching, everyone at home. We'll see you in approximately 167 hours. But until then, have a lovely evening and have a nice week. Bye.